Okay, hello everybody. First of all, thank you very much for this opportunity. It's a pleasure to speak about this very important topic. Um, and I wish I was there in Berlin. Berlin is a special place. In fact, about 10 years ago, when I was actually in Berlin for my sabbatical, is when I started to think about you know informatics, machine learning, etc., as they apply to material science. So it's a pleasure to be here to present this lecture. The way I'm going to do it is there are going to be two parts to what I'm going to discuss today. Part number one is going to describe how a material science and engineering person views views machine learning, how they are beginning to use machine learning within their workflows. It will be a high-level overview of how this machine learning pipeline is being built and used. That will be part one. And I think this part one should take about 25 minutes or so, and then we'll have a break. And then after that, part two will be a deep dive into a specific application and implementation of the machine learning workflow, but within polymer science. So that will be my deep dive description of how we are putting an ecosystem, a capability together. So that'll be part two, right? So those are the two things. During the course of my presentation, if people do want to interrupt me and ask a question, that is fine. I will probably also pause now and then to see if there are questions. But the plan is to finish the first part and then have a 5 or 10 minute segment for discussion. So this is my first slide. I also want to point out that we recently published an article that has the same title as that has the title down below: Emerging Materials Intelligence Ecosystems Propelled by Machine Learning. It's a long review. It's like a 25-page review, but it summarizes a number of things that are happening within the material science and engineering field, overlapping with machine learning, informatics, etc. Let me start off with a very, very basic bird's eye, very high level overview of how we could look at these informatics methods as they apply to real materials discovery. You see here a cartoon of a table, right? You have a number of cases, case 1, case 2, etc., case n. And for each of those cases, there are x1, x2, etc. values, and then there is a y value. The x1, x2, etc., the x vector, in other words, actually describes each of the cases, right? It provides a mathematical, numerical description of each of the cases. And y is some attribute, some property of case 1 that we would like to be able to predict eventually. We assume that initially we have all the x values and the y values for cases 1 through n available, right? And if they are available, you can actually put them in a table like this. And the question is whether we can make a prediction for the y value of a new case, case n plus 1. So for case n plus 1, we can find out what the x vector would be. And then based on that x vector and based on the data of cases 1 through n, we would like to make a prediction of the y value. So that's the idea. Now, the x vector has many different names. It could be some community call the x vector as a feature vector. Computer scientists, for example, call the x vectors as feature vectors. Some people call them as fingerprints. Some people call them as descriptors. They all actually mean the same in the sense that they're all some sort of a numerical representation of each of the cases, right? For example, if you are in the healthcare care informatics field, your X vector could be symptoms of some affliction that a patient has, right? Or if you are in the material science field, these could be attributes of a material, right? So that's what X would represent. And Y, if you are in the healthcare field, Y would be the status of the disease, whether you have the disease or not, or what stage of the disease you are in, etc. And if you're in a material science field, of course, the y value is actually a material property, could be a material property, right? So I'm trying to motivate what x and y could possibly mean. Another thing is y can be numerical or categorical, meaning y can be a bunch of numbers, either discrete or continuous, or it could be labels, right? Yes or no. It could be binary or ternary, whatever labels, right? So that's the form of this sort of arrangement of the data. Let's get a little bit deeper on the X vector, right? Or the fingerprints or the set of descriptors. Now, what should X be for a case, right? That is a very, very good question, and it's not at all obvious upfront what X should be. In fact, creating the X vector, finding out the appropriate descriptors is the main part of this entire workflow. This is actually the most fun part, the most challenging part, and the most critical part of this entire workflow, right? And this is where your past experience and domain expertise actually comes in. And of course, these days there are also attempts to create X with very little domain expertise, but we may talk about that later on. But in general, your X vector is determined by is determined by the domain expertise, right? And of course, there's another question as to which components of X are truly relevant to Y, right? Which components of X are truly relevant, and maybe some components of X are redundant, so the challenge is to first come up with all the components of your X vector, and then determining which subset of that components are relevant for the problem you're trying to study, right? This process is called feature selection or feature extraction or feature reduction. There's a lot of jargon within this field, and I'm sure that in the past lectures I took a look at the other lectures that are preceding mine, and you've already been exposed to a lot of the nuts and bolts and details. But the point is that there is a fair amount of jargon, right? And here are a couple of more jargon. If we have this table for cases 1 through n, and for case n plus 1, we would like to make a prediction of the y value. We call that a supervised learning, right? So that's called supervised learning. On the other hand, let's say you completely ignore the y column, and you have just the x matrix. And you want to see if there are patterns, if some of the cases are clustered in this X space, and they belong to one class, and a different group of different subset of the cases belong to another group. We call that as unsupervised learning or classification, right? Based on X alone, can we do some analysis? That's the question, right? That's what an unsupervised learning person attempts to do. Okay, so what I've presented so far is some sort of a very, very high level bird's eye view of how we may look at a data-driven approach to discovery. Here is a little bit in-depth stuff that relates to material science. So you see, as I said, as I alluded to upfront, machine learning, at least within the materials community, is used loosely. The expression machine learning is used a little bit loosely. It may refer to data mining. It may refer to what is called a surrogate modeling. Okay, or materials informatics is another expression that is used. A lot of these expressions are used interchangeably. But the common theme for all of this is that we use data, prior data, either data that is already available or data that is systematically created. Essentially, these are all data-driven approaches to design, discovery, development, understanding. So this top picture over here that you see, right, is the traditional approach, right? Let's say you have a new material you want to study. One approach is to make the material in the lab and make measurements on those materials, and then on that material, and then you have an understanding of that particular material. Or you could do computations. I'm a computational material scientist. So in my group, just like with Professor Scheffler, we do a fair amount of calculations at different scales. So you could take a material and then do calculations on it and produce data, right? Regardless, you start with the material and then you produce results, data, measurements experimentally or through laborious computations. And let us say you go through this path, this workflow, this pipeline, left to right, right? Material to property, materials to observations. Many times for a lot of different materials. You would have accumulated a data set. And the question is whether you can use that data set to go from left to right in a far more efficient manner than you can with traditional experiments or computation. And in the process, can you also tease out some knowledge and understanding? So that's the whole process. And of course, this fingerprinting, as I mentioned earlier, is key. And that is why I'm kind of teasing that out of what I've discussed so far and putting that there. This representation, numerical representation of materials is the most important part in this entire workflow when you go from left to right, when you use data-driven approaches. Okay, with that understanding, now let us go a little bit deeper. Here is a table, very similar to the table I showed earlier in the first couple of slides. Let us say you have a number of materials, material 1 through material n, for which we know some property P, right? P1 through Pn. We have this data set. Let us assume that we have this data set already, meaning we know the property values, either computed or experimentally measured, for material 1 through material n, right? And then we ask this question: for a new material X, which has not been seen before, which has not been studied experimentally or computationally before, what is its property value? Can we use this data set in part A of the slide, this data set alone, to give an answer to this question? Turns out that we can, but as we can anticipate, we have to go through some steps here. First step is, of course, representation of each of the materials in terms of these fingerprints or numerical vectors or descriptors. And then the second step is mapping those descriptors, those vectors, numerical vectors, to the property values. And that's what we call as the learning step. There is a fair amount of art and experience that goes into coming up with the right representation, the right fingerprinting scheme, and also a fair amount of experience that goes into coming up with the correct learning algorithm. The learning algorithm is nothing but a mapping, function finding step, right? We are trying to relate P to the F vectors, and we are trying to find an approximate function, a hypothesis, a mathematical hypothesis that connects the fingerprint vector to the property value. And once we have that, we can answer this question, right? What is the property value of material X? So that's the basic idea. Now we are going to drill down into some details, right? Let me pause for a minute here and ask if there are any questions from anybody. And I'm also going to look into the chat part. Okay, nothing so far. All right, I'm going to keep going. So now let us take a look at this entire machine learning pipeline, right? For within material science, at least. The first step is, of course, data curation. You need to have data. Without a proper data set, you can't proceed. And then, of course, the next step is fingerprinting. And then after fingerprinting is this learning step, which will lead us to a surrogate model that connects the fingerprints to the property values. And then once you have a surrogate model, we can make property predictions instantaneously. And if we are able to go through from left to right smoothly, then we have a predictive scheme. We can also in the process extract some knowledge. And I'm going to show some examples in the second part. Okay, so let's now talk about the first part, right? The data curation aspect. So now I'm going to just to make it interesting, I'm going to ask a question to the audience. What could be some sources of data we could use, or material scientists could use, in your opinion? Okay, so here is one possible source. You can actually use data from your own computations or your own experimental measurements, basically from your own lab, or you could work with a collaborator who produces the data for you, right? So that's one source of information. Another source of information is obtaining data from the literature, right? Either the old-fashioned human manual way of mining data from the literature, Or these days, there are also methods that are becoming available, and we are actually developing one such thing. For example, using natural language processing to extract data from the literature automatically. Right? And of course, there is also historical data that may be sitting in lab notebooks, calculations you may have done in the past or experiments you may have done in the past, but that led nowhere, right? It led to nothing interesting or exciting, so you kind of put it away. You did not publish it. You did not even discuss it much because it was not very exciting. And you put it away in your lab notebook and it's just sitting there. These could be classified under failed experiments, right? Failed experiments or failed computations, or uninteresting experiments or uninteresting computations. From a machine learning point of view, a cool or successful result is actually as important as a not so interesting or failed result, right? So because the machine wants to learn all parts of the spectrum, right? So that's some sources of data. And another big source of data are repositories that are becoming available, right? And you probably are already familiar with some of them. You had already a couple of lectures on Nomad, which is which you folks are very familiar with. This Scheffler and Draxel are people who have been behind that. But anyway, so here is a very rough and incomplete list of data repositories that are out there for material scientists. The first block, the stuff in the top part, those are mainly experimental databases, right? Databases that contain experimental measurements, right? That's what is up here. And then the stuff down below are computational databases, and Nomad is up here, right? I believe that's the biggest one today. And then there is AFlowLib, OQMD, etc., Materials Project, and so forth. So you could actually draw on data that is already out there, or data that you produce, data that's available in the literature, data that's available in repositories, etc. Now, okay, so now let's talk about, okay, well, there are these sources of data, but how do we organize them? How do we curate them? How do we collect them in a manner that becomes useful for this workflow, right? Let us say you're interested in complex oxide materials and you're working on, perovskite-based photovoltaic applications, for which one critical property is the band gap of these materials, right? So your database, the database that you are going to construct for your problem could look like this, right? Your listing of complex oxides, perovskite type complex oxides, and their corresponding band gap values, either computed by somebody or maybe measured experimentally, right? So that's, you could have a data set like that. You could create a data set like that, either from the literature or from your own measurements or calculations, or from repositories. You could create a database like that. Another way of another possibility is you may be interested in a different material class like polymers, right? So if you are into polymers, you will know that one of a important property of polymers is this thing called the glass transition temperature, right? This is a temperature above which the polymer is rubbery and below which it is glassy, right? Brittle. So it's an important attribute of polymer. So, okay, you may want to create a model that can make predictions of the glass transition temperature of polymers. If that was the case, you need to assemble a data set of a variety of polymers and their corresponding glass transition temperature values. It could look like that. These are just examples of how your data set could look like, right? Or maybe you are involved in material synthesis work, and you subject your materials synthesis process to a variety of conditions like temperature, pressure, and various other parameters, process parameters, the reactor parameters that you actually use to make your material, and you record it very systematically, right? Under these conditions, you get a good sample. Under these conditions, you get a poor sample. Under some other conditions, you get a mediocre sample, things of that nature, right? So you could actually assemble a data set of that type, right? Or you could be involved in some in catalysis work, where you consider a variety of catalysts, right? Yeah, catalyst A could be platinum nanoparticles of a particular size on some substrate, silica substrate, and catalyst B could be rhodium nanoparticles of a different size in a different substrate. and so forth. And then you're testing these different catalyst systems for a particular chemical reaction process, right? Whether it has high selectivity, whether it has high activity or low, etc. Right? So you can assemble a data set like that. So these are all just examples. I'm trying to cover a variety of examples that a material scientist may actually be interested in, for which they first need to organize their data. Right? Okay. Now let's now switch to the fingerprinting aspect of this problem, right? So as I said, this is a very, very critical step. Just to remind everybody, we talked about the data set. We just assembled the data set. This is what we discussed in the previous slide. And then the next step is, of course, to represent each of these materials into these fingerprinting, right? So that's what we're going to talk about right now. Now, this is a fairly complicated exercise. In other words, going back to this this example set of data sets, what we are trying to do now within the fingerprinting process is we are trying to find out how we can take these take the stuff on the left columns of each set, right, and represent them numerically. In other words, we want to convert each of these cases to a X vector, right? And with the goal being that we want to map the X vectors to the last column, which are these columns, right? That's the idea we're trying to get into. So ultimately, we would like to establish a mapping between X and Y, but first, what should X be? Right? Okay. Now, this is a fairly involved process. This is a step that requires a lot of thinking and a lot of effort. This is perhaps where most of the effort will go in. So some thoughts and very high level general comments about this fingerprinting process itself, right? Again, just as a reminder, this is a numerical representation of a material, process, or case. It's also referred to as a feature vector or set of descriptors, as I mentioned earlier. The point is that these components of this X vector or these descriptors should be easily computable, or they should be already available attributes of the material, process, or case. If they are very difficult to compute, then you have completely defeated the purpose of creating an efficient model to predict your ultimate properties, right? So the fingerprint components should be easily accessible. They can vary in length scale, right? They could be at the atomic level, they could be at the fragment level, or they could be at a macroscopic scale, depending on the problem of interest. They should be invariant to certain transformations. You rotate the material, the fingerprint should not change. So that's what we mean by invariant. But invariance is actually too stringent, too much of a constraint. Some people also call it as equivariant, because there are some properties which should indeed vary with certain transformations in a particular way, right? So equivariant is the expression that people use. In any case, the fingerprint should obey certain rules of transformation. That's the point I'm trying to make. I think you probably have encountered this aspect already in a couple of lectures before. Of course, the fingerprint should not contain irrelevant components, but we do not know this ahead of time. Right? As I kept emphasizing, this is the most critical part of this entire pipeline. This is where you need experience. And this is also where you develop experience, right? It's during this process that we actually learn more about our own problem ourselves. Okay, I am now going to step through a few examples of fingerprinting, right, at different scales. So we're going to start at the large scale. This is work that actually what I'm going to give a very high level bird's eye view of a very high level way of fingerprinting or coming up with descriptors. And interestingly, this what I'm going to talk about now in this particular slide, it actually originated in Berlin. In Professor Scheffler's group, Luca Giringelli was one of the first people to actually look into this problem, and like 5 or 6 years ago. And since then, there has been a lot of very exciting developments that built on that work, right? So okay, so here is an example, right? High level, you may want to predict a very complex property of a material. It could be, for example, what is the crystal structure of a material, or it could be, hey, what is the fracture toughness of a material? These are highly complex properties that are determined by multiple factors, and we don't even know what all the factors are and how those factors are related to the ultimate thing that we are trying to figure out, which is namely Is the material a superconductor? Is the material a good thermoelectric? Is the material, what is the crystal structure of this material? What is the breakdown strength of the material, right? So in order to do that, we start with certain basic primary features, right? Such as the band gap or dielectric constant or density, bulk modulus, easily accessible features of the material. What are the covalent radii of the elements that make up the material? Things of that nature, which are easily accessible features, right? And then what you could do is you could start with those features, and then you could actually use these prototype functions, what are called, I believe Luca called them as prototype functions in his first paper on this topic. You use these, basically start with these primary features, and then you produce secondary features, right? For example, what do I mean by X here? This is different from the other X we talked about. EG is taken by itself, and 1 over X basically means EG is the reciprocal of EG is taken, 1 over EG. This is square root of EG. This is 1 over square root of EG. This is EG squared, etc. Right? So use these prototypical functions and operate them on each of these primary features, and you get new functions. And now you can multiply them. You can create compound features of varying levels of complexity and sophistication, right? And so at the end, you will have hundreds of thousands, millions. I believe the Fritz Haber group is working on situations where they have millions or maybe even billions of functions, right? You can produce a lot of compound features, and then you go through some sort of a down selection from there on, right? So if you want to know more about this, you can refer to this paper. I believe this is the first paper that talked about this kind of a approach for material science problems. And also there are subsequent papers after that where a method called CISO has been used. I believe that there may have been lectures already as part of the series where such methods have already been discussed. So this is one approach, right? This is one way to produce your fingerprints or descriptors. High level, you start with high level, easily accessible features of materials, and you operate on them with various operators, and you combine them in different ways, and then you down select the most optimal small subset that correlate best with the property of interest. That's the basic idea, right? Here is another way that was to a large extent, it came out of my group, and this actually deals with fragments, and we did it for the example of polymeric materials, right? Polymeric materials, as you know, are made out of molecular fragments and organic fragments, and these are some examples of fragments that could occur in a given polymer. And so, we can, when you have a new polymer, we look at that material and then say, okay, how many fragments of the first type do we have? How many fragments of the second type, etc., etc. So we have a big catalog of fragments that can potentially occur in polymers. And then it's a bookkeeping exercise. And then when you have a polymer of interest, you go to your catalog and figure out how many times each of those fragments occur in that polymer of interest, and you use that to create your fingerprint, right? So yeah, your fingerprint vector may look like this, where a particular component can correlate to the number fraction of fragment of type 2, because it's the second component of the fingerprint, number fraction of type 2. Right? So that's another way to fragment it. So the first way starts with the easily accessible macroscopic or other properties of intrinsic properties of materials. The second one goes down to the atomic, or not exactly atomic level, but molecular fragment level. And then you could go down all the way to the atomic or subatomic level of resolution, and you can actually represent materials using features that describe how atoms are arranged in materials, right? Molecules or materials, right? So you start, for example, with the reference atom, and then you may clamp Gaussian, three-dimensional spherical Gaussians around that reference atom, and you keep track of how the neighbors around that reference atoms are arranged as captured by these Gaussians. And then you can get more and more sophisticated with it. There are many, this is a very active area of research today, right? So this kind of an approach is ideal for capturing atomic level properties at a very high level of accuracy, and also for capturing and encoding crystallographic information. Right? These are three very quick examples of how one may go about fingerprinting fingerprinting materials. Okay, I think there are a few questions in the chat. Maybe I will pick them up. Hold on just a second. I need to switch my laser pointer. Okay, the first question is, in general, these primary features would come from experimental data. Great question. So they do not necessarily have to come from experimental data. Some of them can come from experimental data. Some of them could be heuristic rules that are available. For example, they could be covalent radii. They are really a combination of experimental as well as some calculations. They could just simply be computational data also. So again, it takes a fair amount of domain expertise to figure out what is the right set of data to actually start off with, right? Okay, next part of that question, I'm asking because sometimes we would like to skip the cost part of computing electronic properties to build the representational material, I think. But if the fingerprint depends on calculated data, how to avoid this expensive part for a new material? Great question. Yes. So as I mentioned earlier, we want to use features that are easily accessible, right? So this could be data that's already calculated by somebody else. So if you need to do a fresh calculation, if making a prediction for a new case mandates a fresh calculation, that kind of in some sense defeats the purpose, right? On the other hand, if the fresh calculation is cheap, much cheaper than the ultimate property that you're trying to predict, it may be okay. So this is something you may have to figure out based on the problem of interest to you. Okay, so those are the answers to my to the questions that just came up. I'm going to keep going, and then I'm going to finish up, and then we'll take questions at the end. All right, so let me now go to the last segment of my talk of this particular part and wrap up. Good. So here is a slide you've seen before, the tables and the fingerprinting and all that. So now we're going to talk about learning, this last step, right? Assume that we have our data set. Assume that you've come up with some suitable representation, and now you're going to go into the learning exercise. I'm going to be sort of superficial on this point because I know that a number of these learning methods have already been discussed in a very detailed manner in many previous lectures, right? So just as a review, there are many ways of mapping your X vector to your Y values, right? The most straightforward and first place to start method is linear regression, right? And of course, there is this really nice fancy method, lasso, and also CISO, which I very briefly mentioned earlier, which allows you to find the correct small subset of your full fingerprint components that are best correlated in a linear sense to your Y. And there is this method called K nearest neighbors. Very simple, very intuitive, also very powerful, right? So K nearest neighbors basically means that when you want to make a prediction on a new case, you find the known cases which are most similar, the K most similar cases to the new case of interest. And then you basically simply find the average of those, the Y values of those K cases, right? So the K cases that are most similar to the new case of interest are called the nearest neighbors. And and the idea is that similar cases will have similar properties. And so the new case is the case for which you want to predict the property value. You find K cases that you already know for which you already know the Y values that are most similar to your new case, find the average, and that's your K nearest neighbor method. Kernel ridge regression or Gaussian process regression, they are both very similar, although philosophically slightly different. But the idea again is these are both extensions or sophisticated versions of the K nearest neighbor method. Instead of just considering only K, you consider all the cases that you have seen before and find how close, how similar or dissimilar your new cases to all those cases. And then you find a weighted sum of all the Y values of the old cases, and you come up with an estimate for the new case, right? Another class of methods are random forests and decision trees. I believe there was a lecture on this earlier. And then, of course, neural networks. I believe there were a couple of lectures on deep learning just recently in this lecture series. And of course, there are many more, right? In fact, there are just too many. And that's where the confusion comes as to what to use, right? Exciting, very exciting frontier. So in the interest of time, and because I also do not want to repeat what others have said already, I'm going to just use two more slides to actually summarize two methods: the Gaussian process regression and the neural network approach. Right? Just this is just intended to be a refresher. Okay, so you see, we started off by saying that, okay, we have a bunch of fingerprints for cases 1 through n, and then we know the property values. Now here, this picture that you're seeing over here, shows in red, the red spots that you see, 1, 2, 3, 4. Those are cases for which we already know the property value p, right? And what is shown here is a fingerprint space. If you have m components in your fingerprint, this is actually an m-dimensional space. And in this m-dimensional space, each of these cases is just a point, right? 1, 2, 3, 4. These are points corresponding to the cases for which you already know the property value. And case I, the green point here, is the case for which you want to make a prediction. You don't know what the property value is. You want to make a prediction. So you find the distance in this fingerprint space between your green new case and all the cases that you've seen before. And based on the distances which are represented as d, you estimate the value of this case here through a weighted sum of the y values of all these other cases. That's what is shown mathematically over here. Very intuitive. It's one of my favorite methods, and it's become very popular within the community and very powerful. But one thing to keep in mind is that this method actually scales poorly with the size of the training set, right? Because there is an inversion of a matrix that's involved here. And for that reason, the training process involves, it scales sort of poorly with the training set size. And even prediction actually scales linearly with the training set size. So as long as your training set size is not that big, this is a great method. Very intuitive. It also gels well with our own human thinking. When your training set size is enormous, you may have to go into other methods such as deep learning, right? Based on neural networks. Once again, this is the data set that we assume that we have already, fingerprint vectors and property values that are known. And you have your neural network over here. It has an input layer, and then it has an output layer. In this case, the output layer is just one node. And then, of course, there could be multiple hidden layers. What you supply to the input layer are basically these fingerprint values, right? If you have m components, you could have m nodes in your input layer. Each of these values gets applied to each of the nodes, and the output value is required to be the corresponding p value, the property value, right? And in this manner, and you have a lot of details over here called weights, activation functions, things of that nature. Essentially, at the very heart of it, what you're really trying to do here is you're trying to find a highly non-linear mapping between your f vector and your p. It's really a function finding step where you have enormous data, and so you could have enormous number of parameters over here that you use to establish a very solid nonlinear mapping between your input and your output. That's really all I will say about this at this time. You have seen a lot of details in the past already. Okay, to summarize, this is the workflow, right? You go from data curation to fingerprinting to your learning algorithms to your property prediction scheme. And you assume that you have a data set first. You want to ask this question: what is the value of a property of a new material X? You have to go walk through these steps. And if you go through all of this right, then you have a beautiful prediction model at your disposal. And if everything goes well, and if we have a fair amount of data of this type, either computational or experimental, and then we do have a very good shot at coming up with these surrogate models which can significantly accelerate predictions, property predictions, and ultimately discovery. Okay, so that's it. I'm going to stop there. And here are some articles that have come out from my group over the years. This is something I mentioned earlier. This is something that just came out. It's a comprehensive review. And then here are a few other articles touching on different types of problems within material science. Thank you. I'm going to stop there. I think we are in good time for maybe a 5-minute, 5 to 10 minute, break, discussion, etc. Okay, All right. So great questions. So the first question during this time is, if you use deep learning methods, if you use neural network methods, um, can you just supply the primary features, and can the system automatically figure out what the equivalent of the secondary, tertiary features would be? The answer is yes, right? Because it is a nonlinear model that the neural network tries to identify that best maps your input to your output. And so, yes, the primary features is what you would, in principle, supply to figure out this mapping. The one thing to keep in mind, though, is that neural network methods are best used when when your data set size is big. Otherwise, there is a huge danger of something called overfitting. And when your data set size is small, which is common in many material science situations, you're actually better off by handcrafting your secondary, tertiary features, right? So that's the distinction. If your data set size is small, be careful what method you use. Neural networks, deep learning is probably not the right approach. You're better off handcrafting stuff. Whereas if your data set size is enormous, then you can let your neural network figure out the map, the nonlinear mapping. So second question. So in the ML pipeline shown in the slides, we go directly from the numerical representation to the modeling part. But sometimes people also do some kind of data pre-processing between these two steps. Is a step in the context of material science, and which kind of data processing should we adopt? Great question. Absolutely. So this data pre-processing comes in different flavors and forms. I'm actually going to talk about very briefly one of that, I think, in part two. The data pre-processing can actually involve, for example, curation, establishing the veracity of the data set. That is one. The other thing is what subset of your fingerprints are redundant, irrelevant, things of that nature. There are quicker ways to actually figure that out. You could do principal component analysis, for example, to figure out how to reduce your fingerprint dimensionality. And there are other related methods as well. You can use recursive feature elimination to eliminate some of the features that may be not relevant or may be redundant. So yes, the data pre-processing is actually an important part of this workflow as well. I just try to make it simple in the first part. I hope those are satisfactory answers. If people have further follow-up questions, please let me know. So as I mentioned earlier, now I'm going to do a deep dive into a particular application, something that we have been working on for many years now. We are really in the process of creating a Polymer informatics ecosystem. And the idea is to be able to use these data-driven methods to quickly make predictions of a variety of properties of polymers, and also solve the inverse problem, designing polymers that meet target property requirements. This is a story that has unfolded over many years, as I said, and many contributors and many sponsors over the years. And there is this very recent paper that we just published by the same title as this title of this part 2 segment, Polymer Informatics Current Status and Critical Next Steps, which sort of captures this ecosystem that we and many others in the community are in the process of building. Okay. So before we dive into the main substance of this presentation, I'm going to start with a couple of thoughts, right? Some challenges that materials development people actually face. One of the challenges is that selecting a material or discovering or designing a new material that meets certain property requirements or performance requirements for an application is non-trivial. And one of the reasons for this non-trivial nature is because a lot of times we have conflicting property requirements. I'm going to use one example over here. Let's look at the picture on the far left. What you see there is actually a snapshot of a capacitor bank that you would find in a hybrid car or electric car today. Of course, battery is the most important thing for a hybrid or electric car, especially electric car. But then the battery is not quick enough to grab the energy during the braking process. So when you brake a hybrid car or electric car, the energy is first sent to the capacitor bank that you see over here, because capacitors are super fast. And then the energy gets gradually released to the battery, right? So what you see on the left is a capacitor bank. Today's capacitor materials are made out of a material called polypropylene, polymer called biaxially oriented polypropylene. And these dielectric materials need to have for this material to store a lot of energy, electrostatic energy. You need to have high band gap and high dielectric constant, it turns out. But these two properties are sort of inversely related to each other, right? So that there is your challenge, right? How do you create a material that has both high band gap and high dielectric constant, right? And the item in the middle is a picture of a solid state battery electrolyte, where the solid state electrolyte could be a polymer, which can shuttle these lithium ions or ions from one electrode to the other. And for this polymer electrolyte to be a good electrolyte, it has to, of course, have a high ionic conductivity, which basically translates to the material having a low glass transition temperature. But it also has to have a high mechanical strength, for which you need a high glass transition temperature. You see, so again, you have two properties that are unfavorably entangled. And the example on the right is yet another case where you need a couple of important properties for organic electronics or flexible electronics applications. You need a low band gap, and you also need low carrier recombination, and these two are inversely related. So when you have these kinds of situations, when you have property requirements that are undesirably entangled with each other, properties that are undesirably entangled with each other, you may have an issue, right? And that is further compounded by the search space. You're trying to search the materials chemical space to find the optimal candidate that has the best combination of these property requirements. But then you need to search this daunting space, right? This one slide here, one slide picture attempts to capture the expanse of the polymer chemical space. Polymers can be, linear. This is the simplest of them all, polyethylene, and a close cousin of polypropylene, which I briefly mentioned earlier. And these are other linear polymers, and you could have cyclic, homocyclic, heterocyclic. You could have mixtures of aliphatic linear chains and cyclic, and you could also have non-carbon based species in the backbone of the polymer, silicon, germanium, tin, and even other metals, iron, ruthenium, etc. So the space of polymers is really truly spectacularly staggering. And the question is, where do we start? How do we do this search efficiently, right? One of the problems we have worked on for many years now is to find if there are good replacements for biaxially oriented polypropylene for this capacitor, energy storage capacitor application, right? So this is a picture I already showed earlier. The material of choice today is biaxially oriented polypropylene, as I mentioned. And this is a remarkable material. This is the second most produced material on Earth right now, second only to polyethylene, right? Polyethylene is the material that is mass produced to the greatest extent today. And then after that comes polypropylene. It's very cheap because of that. And it has a very high, it's a great, remarkable insulator. It has a big band gap, which translates to a very large breakdown field. Meaning this is the highest electric field that the material can withstand before it breaks down, right? 700 volts per micron. It has a very low dielectric loss. And what that means is that pretty much all the electrostatic energy you put in, you will get out, right? The dielectric loss factor, loss tangent is 10 to the minus 4, which is a remarkably low number. But there is a problem. The problem is that this material has a very low dielectric constant of about 2.2. This translates to an energy density of about 5 joules per cc for this material, right? This is the maximum energy, electrostatic energy you can store in this material per volume, right? 5 joules per cc. This is an important number. Let's keep this number in mind, because Whenever you want to design a new material that is better than this, you want to make sure that that material has a higher energy density than this standard material, right? So this is the figure of merit that we are going to keep in mind. The maximum energy density, the maximum energy you can store in a dielectric material is in a linear dielectric material is given by this very simple looking formula, right? Dielectric constant times the square of the highest electric field the material can withstand, right? So basically this means that if you want to come up with something that is better than polypropylene, you need to find something that has a higher dielectric constant and preferably a higher breakdown strength, breakdown field than that of polypropylene. Easier said than done. But anyway, here is the screening criteria in a slightly different form. We want to search and screen the chemical space of polymers for materials with high dielectric constant and large band gap. I should really say high breakdown field, but because we don't have a rigorous, solid computational method to compute the breakdown field for real polymers, we use the band gap as a proxy because there is favorable correlation between band gap and breakdown field. So we're going to search the space for high dielectric constant for materials with high dielectric constant and large band gap, right? And of polymers. So we started off years ago. We started off with this cartoon, this representation of polymers, a linear chain. This is the repeat unit. That's why there's these brackets with the n there. That section keeps repeating in space and creates an infinite chain or a very long chain. And each of these blocks could be populated by one of many chemical species. At that time, 7 years ago, when we started to work on this problem, we assumed that these blocks can be, either one of these 7 possibilities, because these are very common blocks that people use. If all of these blocks was CH2, you would have polyethylene, right? But then we allowed for all these different combinations. And so this led to, hundreds of possibilities. But today, at that time, we started off with 7 possible blocks, chemical species, but now we have thousands that we are trying out. Now, when you consider these 7 blocks and make your hypothetical list of polymers, turns out that you will have a few hundred cases that are kind of unique. And then for those almost 300 cases, we did DFT calculations to predict the dielectric constant and the band gap, right? There are probably DFT people in the audience. For those aficionados of DFT, I want to mention that the band gap was computed using hybrid exchange correlation functionals, and the dielectric constant was computed using density functional perturbation theory. Both fairly expensive methods. And what makes it even more expensive is that in the first step, we need to do this thing called structure prediction. Because for a new polymer, we have no idea what the structure is to begin with, right? And so we need to first predict the structure, followed by prediction of these properties. The immediate thing that jumps to your eye is that there is an inverse correlation between these 2 properties, right? You see, this is the undesired entanglement of properties that I alluded to earlier. We really want high dielectric constant and high band gap, but you see the inverse relationship. This is a log-log scale. So you can fit if you look carefully, you'll see that you can fit a line which has a slope of -1 in this log-log scale, meaning that dielectric constant is inversely proportional to the band gap, right? So we were initially dejected. We thought, what do we do? You see polyethylene, polypropylene is down here, large band gap and low dielectric constant. And if you go to the other end of the spectrum, you have the conducting polymers, low band gap and high dielectric constant. Most of the dielectric response comes from electronic response. So those are the common conducting polymers. But for this application, we want high dielectric constant, high band gap. So we kind of felt dejected initially, and then we thought, oh, you know what? Maybe we don't need super high values of both these properties. Maybe moderate values of both would be good, right? Trade-off. Let's do a compromise of the 2 properties. We identified 3 cases, right? These are the 3 repeat units for the polymers that we proposed. The bottom one here is the urea, NHCO, NHC6H4. It's what you use to make fertilizers. We were proposing that we make a polymer out of this urea, polyurea. And this is in this case, the CO is replaced by CS, which is a thiourea. So basically, that's a polythiourea, and this is a polyimide. So these are recommendations we made to our experimental colleagues, and we had very talented and very enthusiastic experimental colleagues and grad students who actually made these 3 polymers, tested them in the lab. And what you see over here is a comparison of what we predicted for these polymers. That's our prediction using DFT. Stuff outside the brackets, and the stuff inside the brackets are experimental measurements on these 3 polymers: polyurea, polyimide, polythiourea. And as you can see from the numbers, it was favorable correspondence, and we were super excited, right? So we rejoiced. We thought, oh, we have been successful in translating ideas from the computer to the lab. But there was a little bit of a hitch. And the problem was that none of these 3 was useful from a practical point of view. They could not be processed into flexible thin films, which is what you need to roll this up into a capacitor material. This is sort of where the ingenuity of my experimental colleagues came in, right? So what they did was they started with our recommendations. These were our 3 recommendations originally made. They actually made tweaks to them. They added linkers and side chains and other species in the main chain. And they were able to make several dozens of polymers that are inspired by the computational recommendation, but also now processable, right? Many are processable now, and I'm going to show 3 examples, right? These are 3 examples of polymers that we call as 2nd generation polymers. 1st generation are the ones we proposed. 2nd generations are the tweaks based on what we proposed. And this is the biaxially oriented polypropylene, the standard material. These are the properties of those: dielectric constant 2, breakdown field about 700, energy density 5 joules per cc. That's the figure of merit we want to keep in mind. These are 3 new polymers that we were able to make in the lab, and these are actual pictures of actual films that were made, and breakdown measurements were made, 10 micron films, very exciting. Dielectric constant 2 to 3 times that of polypropylene, and breakdown strength, breakdown field about the same or slightly better than that of polypropylene, translating to energy density of 2 to 3 times that of polypropylene. So we have a few materials now that are clearly superior in terms of performance to polypropylene. And so we are kind of going through some scale up now of some of these materials. Right? So it's a very exciting story. And this is a picture I showed. This is a chemical space that we wanted to search for using our search criteria, using DFT. And really it is a synergistic collaborative work with my experimental colleagues, Greg Sotzing and his students, and Yang Cao and his students. We got a few hits, but of course we were also lucky, right? We kind of knew which part of the space to focus on, and we got a couple of hits. And one story that I just shared with you falls in this area of organic polymers, a story that I'm not going to share with you in the interest of time because I want to move on to the informatics side, is metal containing polymers. You see, these are tin atoms integrated in the backbone of the polymers, right? Metal containing polymers, essentially, which it turns out that they could be even more superior to the organic variety, but they have more processing challenges which we are working on. Okay, at this point, I'm going to pause for a bit and ask if there are any questions.
Hi, Rampi, it's Luca.
Hi. Hey, Luca. How are you doing?
Hi, I'm fine. So it's faster than typing. So I was wondering if you also try to model this kind of lavability, so the fact that you can make the thin film, so like you can predict with some more or less simple descriptor this other property and put it in the machine learning in some way.
Absolutely. So Luca, your question is, can we encode certain macroscopic features like thickness of the film and maybe defects in the film quality, things of that nature, right?
Something like that, yes.
Absolutely. Yes. So this is this kind of takes us into the processing informatics, right? This is something we are very actively working on right now. Can we encode information that is beyond outside of chemistry, right? Chemistry is most very important. We want to capture that, but are there other attributes that we can encode as well? The answer is yes. The question is whether we can collect very reliable data pertaining to that or not, and we are actually in the midst of it right now.
Okay, thanks.
Okay, so now I'm going to switch gears, and then what I'm going to do is in the next 20 minutes or so, 15, 20 minutes or so, I'm going to now, pivot and go down the informatics route, right? One of the questions that my experimental collaborators would come and ask me is, here is a polymer we can make. Can you tell me what its dielectric constant would be? So I would tell my friend and colleague, Greg Sotzing, Greg, give me 2 weeks. We need to do structure prediction first, and then we need to do these fancy DFT calculations. It'll take us some time. So Greg would say, no, 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 you've done all these hundreds of calculations already. Can you not give me a quick estimate now, like today? So that's one of the things that kind of pushed me in this informatics direction, right? So we have, as I presented already, we have a fair amount of computational data for polymers computed using DFT. And then we also began to accumulate a lot of experimental data on other properties from databases, from our collaborators, published articles, handbooks, etc. So we have a database of several thousand points, polymers for which we have some experimental or computational property. And so, we wanted to use that data set to actually build our machine learning models. Now, I'm going to show you a slide which we already saw a couple of times in the part 1 of my lecture. So, okay, you have a data set. Greg comes along and asks this question: hey, new material, new polymer X, what is its property value? Okay, sure, we can do that, but we need to go through these steps, right, of fingerprinting and then learning, and then we have a predictive model which we can use to make predictions on, right? Fingerprinting, I actually talked about this already in part 1. For polymers, we have our own scheme of fingerprinting or representing polymers numerically. We do it at a few different hierarchical scales. Atomic level, we use these atomic level fragments to keep track of what is happening with respect to very local level chemistry, right? And then at a slightly higher level, we keep track of blocks, functional groups, and so forth, right? So that's the block level, B level, right? A, B, and then C is chain level, even at a higher length scale. How many side chains? Are there side chains? How big are the side chains? How dense are the side chains? What functional groups do you have in the side chains? Things like that. We are working on D and E. Luca just brought up this question of other things, right? Process, other even higher length scale free features. We are actually working on those things. No reason why we cannot encode them. We absolutely can. Pipeline allows us to do that, but we need reliable data to be able to do it. Right? So that is the fingerprinting step, right? The second step is, of course, learning. So I already talked about Gaussian process regression. This is a method we have used a fair amount. We are also using now, because our data set size is becoming big, we're also using deep learning. So we use basically deep learning and Gaussian process regression to build our machine learning models. So here is a picture. Here is a snapshot of some of our predictive models. Let's just simply look at the top left for now, right? Band gap. This is one of the things we started off with. So x-axis shows you DFT band gap values, and there are several hundred points. So in this plot there are 561 points, but today we have like several thousand points. This plot is a little bit outdated already. X-axis is the ground truth, the DFT values for the band gap, and the y-axis is the machine learning predictions of the band gap. You can see that there is favorable correspondence. And likewise, we have property prediction models for several properties. Dielectric constant as a function of frequency, right? Gas permeability across huge, this is a log scale actually. So several orders of magnitude. Permeability of several gases through these polymer membranes. This is actually very important from the point of view of separating mixtures of gases and mixtures of solvents. It's an important problem we are working on. And thermal properties, mechanical properties, etc. You see thermal decomposition temperature, melting temperature, glass transition temperature. Several thousand points are involved in these plots. So we have these predictive models now. If one wants to make a prediction of these properties, the glass transition temperature or band gap or gas permeability, we can make these predictions instantaneously for a new polymer, right? All our models are deployed for the community, free, open access at polymergenome.org, which is a website that we've created over the years and supporting. Here is a short video that actually shows you how one may use this capability. You can type in the name of the polymer or its smile string, or you can actually use this draw feature to build your polymer using a mouse and then hit predict, and then these properties get predicted. So I'm just going to let this movie run for less than a minute. So since a polymer is actually a long chain with a repeat unit, we use the symbol stars and other letters to actually indicate the head and tail. That's the smile string for the polymer. You hit predict, and in a second you will have these properties that are actually predicted, a variety of properties, right? So this is very useful, I believe, for especially for the community, but also for experimentalists who want easy access, quick estimates, statistical estimates for a new polymer that may be of interest to them. In fact, we want to help synthesis people to also synthesis and processing people, in how they choose solvents to either dissolve or precipitate a polymer. And that is why we have a deep learning based predictive model that will also tell which solvents will actually dissolve the polymer. Those are the solvents. And which solvents will precipitate the polymer. These are the non-solvents, right, for that particular polymer. Right? So they can choose a solvent that that works for them and during their synthesis and processing experiments. So that's where we are, but we are also taking baby steps, actually, even bigger than baby steps these days, in a couple of other directions, right? So one thing that I mentioned earlier was, we need to use, we can use manual methods to obtain data from the literature, but it'll be good to scale up that process and automate that process using modern methods such as natural language processing, text mining, figure mining, etc. And we are kind of taking steps in that direction. We recently published an article on one such attempt, which just came out just this last month. And also we are using these AI methods, machine learning methods, to actually plan the next set of computations. As I said, our computations for polymers are in the several thousand data point situation, but we want to scale that up even more, and we want to do new calculations for truly new polymers which are chemically very different from things that we have already studied in the past, right? So we want to use AI methods to actually accelerate the simulation process, accelerate the data production process using simulations, right? And of course, ultimately, our goal is to design polymers, solving the inverse problem, right? We have property targets. We want to design polymers that can that have those property attributes, right? So for that, we're using a variety of algorithms. What I am going to do right now is to show you just two examples. One example of using genetic algorithm to design polymers that meet a target property requirement. Another example of generative algorithm, a generative model approach that generates these polymers with properties that are appropriate using variational autoencoders. Right? And these are two articles that also very recently came out. Okay, genetic algorithm, how does that work? Well, this is actually the oldest technique on earth, right? This is not a new method at all. It is a method that biology, nature uses to catalyze evolution. And of course, in science and engineering, these methods have been used for many decades already to solve several design problems. And here we are using that to solve a design problem for polymers, polymer design. And the idea is, you have these fragments that can make up our polymers. Now we have more than 3,000 fragments that we have in our bucket. And we create an initial population of polymers by randomly choosing fragments and putting them together and creating a first generation parents. And then we use the mutation, we use the crossover and mutation to take one piece of a parent and another piece of another parent, bringing that together and creating a child. And every so often we do mutation, right? Because we want to get out of the gene pool. We don't want to be stuck in the gene pool of the first generation parents. So we use crossover and mutation to create the next generation population, the children. And then we see which of them have the attractive properties we are interested in. We keep only those, survival of the fittest, throw away the rest. They become the next generation parents, and we keep cycling through this, right? Back and forth. And then ultimately the goal, the hope is that we will be able to design polymers that will have the target property requirements. We've implemented this capability, and it turns out to work remarkably well. And here is a goal that we wanted to seek, polymers that have a high glass transition temperature of over 500 Kelvin and a large band gap of over 7 eV. We wanted to see if we are able to design, if the algorithm is able to go to the chemical space that corresponds to these properties, right? You see the picture on the left is just all the points that this algorithm visited through the generations. And as it goes to later and later generations, it kind of converges to this little pocket over here. You see magenta points, 100th generation, that's the magenta point. That's the pocket in this chemical space that correspond to these property values. And these two plots that you see on the right, they show you how the two properties that we are tracking are approaching the desired values as we go from first to the last, to 100th generation. So that is one example, right? That is one example of how we could go about designing. The second example is very new. It's a new capability. It's super exciting. It's based on these things called variational autoencoders. And these are these methods are used quite actively now in other branches of AI, right? And image production, video production, etc. It's quite exciting and also very scary what these algorithms can actually produce, right? You just give instructions on what you want and they can produce the images or videos. How does it work? Well, it has two neural networks, right? One is called an encoder and the other one is called a decoder. The encoder actually takes the chemical structure of the polymers as input, and then it converts that to a point in what is called as a latent space. A latent space is a low dimensional space, a continuous space, whereas the polymer structure, chemical structure space is a high dimensional, and also it is a discontinuous space, right? So each chemical structure, each polymer, each material is actually converted to a point in this latent space. That's what the encoder does. The decoder does the opposite, right? It takes a point in the latent space and makes the structure. It reproduces the structure, right? Recreates the structure. So the encoder does the encoding of the material to a point in the latent space. The decoder does the exact opposite. So you may be wondering, why go to all this trouble of encoding first and then decoding? Consider this. See, the latent space can be viewed as a fingerprint space. And so that space can be connected, mapped to the property values, you see. So if everything is gotten to work well, which is a non-trivial process, by the way, you can go from left. If you want to make a prediction of a new polymer, new case, you can actually go from left through the encoder to a point in the latent space and then go down. That point gets connected to the property value, right? So you can make a prediction. On the other hand, if you want to design a polymer that has a target property value, you do the opposite. You go from property value of interest to the corresponding region in the latent space that correspond to that property value, and then you go to the right. And this way you'll be able to create polymers that will have the appropriate property values. Now, this whole thing is easy to say, describe this way, but it is a very unstable process to have it all trained well, right? So one of my colleagues at Georgia Tech, Lee Song, is actually a pioneer of a new flavor of the variational autoencoder called syntax-directed variational autoencoder, which uses, which incorporates grammar, right? Chemistry. Basically, we teach the encoder and decoder some chemistry so that it just doesn't waste time considering nonsense, chemical nonsense, basically, right? So basically, it's teaching syntax, semantics, and grammar, and some chemistry, basically. And then this process gets optimized, and we are able to do some design. So, so in the interest of time, I'm actually going to skip ahead and just show some results, right? So the genetic algorithm produced some results for this high glass transition temperature and high band gap exercise. And then the syntax-directed variational autoencoder also produced some designs. Two very different algorithms, two things done independent of each other, and they produce designs, hundreds of designs, thousands of designs. And I'm just showing you a selection over here. What is interesting is that there are a lot of common motifs. groups, right? Saturated cyclo groups, or you can find them in both sides, right? Saturated cyclo groups with these oxygens, right? With these oxygens, saturated cyclo groups with these oxygens. Fluorinated, regions, carbon fluor, CF bonds. You see CF bonds over here, CF bonds over there, and there are a lot of common motifs. So both of these algorithms, they have zoomed into the correct part of the or not correct, zoomed into a similar part of the chemical space, right? They've sort of come to the same sort of answers at the end. Super exciting, right? So now we are working with synthesis people to identify which of them are synthetically amenable, right? So we're also trying to encode those into rules so that we want to add the synthetic feasibility as a filter to these design algorithms. So that ultimately what these design algorithms will produce would be compounds, would be materials which are synthetically feasible, easy to make, right? I'm going to finish up. I'm sort of at the end of my time. So this is where we have been for the last several years, but the last couple of years, we've been taking steps in the direction of producing data ourselves using computations, but not in a brute force, high throughput manner at all, but in a autonomous high throughput manner, meaning we tell the DFT algorithm what calculations to do next, those sorts of things. And also we're using, for experimental data, we are building this capability to extract data autonomously, automatically, continuously from the literature using NLP techniques. And on the design side, we're taking steps using a few different AI type algorithms to solve inverse problems. So I'm very delighted to say that all of this work was actually, and I'm just the messenger. The people who actually do the work are highly ingenious, highly creative, highly dedicated. Have the pleasure of working with a number of graduate students, undergraduate students, postdocs, research scientists, and also a lot of people who've left the group and gone elsewhere doing well. And also collaborators, right? There are several collaborators I have to thank, because this kind of work has to involve a multidisciplinarity, computational work, informatics work, deep CS work, synthesis work, processing work, characterization. People getting together in a multidisciplinary setting and solving important problems is very, very critical, and that's probably the way to go about it. And finally, I want to also thank the sponsors who have tirelessly supported our work in the years. Thank you all for your attention. I'm going to stop there, and I'm going to ask if there are questions, and I'm going to take a look at the chat. Okay, there are a lot of questions. That's great. Max's question: to have a first screening of the possible blocks, did you take into consideration if they can be synthesized or not? Yes, good question, Max. The answer is yes. In fact, our first selection of blocks were intentionally chosen so that they would lead to polymers that are synthesizable. What we did was we looked at a benchmark set of like 30 or 40 common polymers. We found what blocks they have, and those were the 7 blocks that you saw earlier. And we then used those 7 blocks to in different mix and match ways to create hundreds of other polymers. About 30 or 40 of those were known polymers, but the rest of them were hypothetical polymers, right? So that's how we started earlier. But now we have graduated from there on. We have like over 3,000 blocks, and these are all blocks derived from a known list of polymers. So at that time, we had a benchmark of 30 or 40 known common polymers, but now we are looking at thousands of polymers that have previously been made. We look at blocks that those polymers contain, and those things work out to something like over 3,000. So that's the answer to Max's question. Next question, Adrian. What percentage of the new polymers you find can then be synthesized and used in practice? Another great question. So if you use our first block of work was done actually purely using DFT, right? So we actually studied about less than 300 polymers at that time, right? But they were very carefully chosen, as I just said, using the blocks that are found in common polymers. So less than 300 polymers. Out of those less than 300 polymers, I would say about a dozen were made in the lab. But it's not just the way to think about it is not what the experimentalists can actually make out of the polymers we select. It is what they can actually tweak as well, right? What computational people, what virtual materials discovery people can do is just point in the right direction. Experimentalists do not have to make exactly the specific thing that we recommend. If they are able to take that as a recommendation and make tweaks that make sense and then make them, that is still, I would call that still as a success, right? So if you now look at it that way, I would say a few dozen polymers were actually synthesized from that batch. Now with the machine learning thing that we are doing, the algorithms can produce literally, there is no limit to how much they can produce, right? They can produce thousands, hundreds of thousands actually. If you let them run, they'll keep on producing. Question is what fraction of those are synthesizable, right? That's a good question. This is why we are actually adding a filter that is based on synthetic amenability, right? So in order to now restrict the search space, restrict the design space, chemical space to those cases that are synthetically amenable. This is work in progress. I believe we can successfully implement that soon. Basically a filter. We need to add a filter to your VAE or a genetic algorithm or other algorithms that you use, so that finally what comes out of the funnel are synthetically amenable. So yeah, I believe we can do that. We can reach a high success rate. Next question, Luigi. How do you deal with molecules of different length in VAE, considering that input-output vectors have fixed dimensionality? Great question. We are not constrained by this at all because of the way we are supplying the input to the VAE. So what we do is we create a table. Okay, the actual raw input is a smile string of the repeat unit of the polymer. Okay, these are not molecules, these are polymers, right? Which means they are really long. These are macromolecules, huge, long chains, but they have a repeat unit. So what we supply to the VAE is the smile string of the polymer. And then doesn't matter how long the smile string is, we create actually some sort of a table. Actually, it's all described in our paper that just came out, right? So the table actually converts the smiles representation to a uniform dimensional representation that the VAE can take. Okay, so it's so there is no limit, there is no restriction on the size of the smile string or the size of the repeat unit. So everything is kind of a uniform dimensional representation gets created, and that is what goes into the VAE. Next question from Max. Some polymers may have different properties just because of the way they pack as a solid. Even if the chemical structure is the same, if there is a way to encode this kind of information into the fingerprint. Another fantastic question. This is correct. Polymers, one of the complexities with polymers is that they are not always crystalline. When they are crystalline, there may be closely related crystal structures. A lot of times they are semi-crystalline, meaning you have regions of crystallinity, and then you have regions where it is amorphous, and sometimes they are all amorphous. So how do we deal with that, right? So we are actually working on descriptors to encode this kind of information. This actually goes back to the first question that Luca asked. Can we encode other kinds of things? We are working with a processing person, one of my colleagues, one of my collaborators, who actually can control the level of crystallinity and the type of crystallinity, orientation of the crystallites, size of the crystallites, things of that nature. We need to produce data for stuff like that. And I believe that once we have data of that type, we will actually be able to encode that and also make predictions that are dependent on the atomic level structure. But that is a little bit down the line. It's a tough problem to solve. What we are actually doing right now is we are making the assumption that our results are sort of averaged over all different structures. Okay, so we are kind of keeping the chemistry as the most important thing and the structure as somewhat of a secondary thing, right? That's kind of the underlying assumption in all that we are doing right now. Those are my answers to the questions. If my answers are not clear, please feel free to text to me or use your audio. Either way, I'm very happy to take further questions. I hope the lecture was interesting and it kind of was complementary to the other lectures that were part of this series. And if anybody has questions, they can also contact me later by email. Happy to take questions and feedback.
Yes, I can say that it was truly complementary also, because we haven't seen such a complexity in the applications up to now in the previous lecture. So I think that's great to have this lecture today.